Okay, we're going to look at the solving an equation. Let's solve t squared y double dash plus 3ty dash minus 8y equals 0, given t squared is a solution using the reduction method. So how do we use, the first thing that's probably going to be asked is show t squared is a solution. So verify that. How do we verify that? We just plug it in. So if t squared is the solution, that means y equals t squared, y dash equals 2t, and y double dash equals 2. And we just plug it in. So in other words, just plug it in here. So 2t squared plus 3t times y dash, which is 2t, minus 8t squared. Does that equal 0? This is 2t squared plus 6t squared minus 8t squared equals 0. So, yep. So we know that the t squared is a solution. Now we want to use reduction of order to find the second solution. So let's have a look at how this works. Okay. So if one solution is, if y dash, or the first solution, if y1 equals t squared, then y2 we are going to say is v times t squared. So this is going to be our second solution. So v times, where v is a function, obviously t squared. And from here, what we're going to do is we're going to need to find out, okay, so y is vt squared, y dash is going to be something, and we're going to use the product rule to find that. So the product rule of this would be t squared times the derivative of v plus v times 2t, written in a really horrible order, but we'll change that. T squared v dash plus 2tv. And we also need to find y double dash, or the second derivative of this. And again, we've got a product rule and another product rule. So the product rule here is going to be t squared times the second derivative of that plus 2tv dash plus this times the derivative of that, which is 2tv dash, plus the derivative of this, which is just 2v. So I think that's right. I've got t squared times the derivative of this, which is the second derivative, plus the derivative times the derivative of this, or that function times the derivative of this, plus the second function, this times, what's the derivative of v? V dash, yep, plus v times the derivative of this, which is 2. So that's all our derivatives done. Now we're going to substitute them into our formula up the top. Now, this is going to get fairly lengthy, but the v's should cancel. Always the v's should cancel. So let's see. So we've got t squared times t squared v double dash plus 4t v dash plus 2v plus 3t times the first derivative, which is going to be t squared v dash plus 2tv minus 8 times vt squared. And we know that equals 0, which is always nice. Multiplying this out, we get t to the power of 4v double dash plus 4t cubed v dash plus 2t squared v plus, 3t cubed v dash plus 6t squared v minus 8t squared v. We know that equals 0. So as I said before, this is 2t squared v plus 6t squared v, which is 8t squared v, minus 8t squared v, which is 0. That's why it's called the reduction of order. We've gotten rid of all the v's. So now what we've got is we've got a bit more simpler equation. T to the power of 4 v double dash plus 7t cubed v dash equals 0. And suddenly it's a little bit nicer, at least, a little bit nicer. Now, what we are going to do is we are going to let w equal the first derivative of v. Okay? So if we write this out, what we've got, and w, remember, so w is d v to t. Okay? All mean the same thing there. So let's put w into here. What we're going to get is 7t cubed w equals 0. That doesn't change. The second derivative of v is the derivative of this, which is just the derivative of that. So we're going to get t to the power of 4 w w dash. So what we've got here is suddenly we've reduced it to a first order differential equation, and one that we can solve fairly easily in this case. So we're going to muck around with this, and of course we'll have to come back to find out what v is. Remember, this is dw to t equals, if we take this over, we get minus 7t cubed w, and let's divide it by t to the power of 4. So we've sort of made it a little bit simpler. We're going to have w to t equals minus 7 over t w, and this is a fairly nice separable equation. What we've got here is a nice separable equation. So let's take the t over here. The t minus 7 over t equals, and take the w, 1 over w to w. And because it's a nice separable equation, we can integrate both sides. When we integrate both sides, on this side we are going to get the log of w equals the log of, or minus 7 outside the log of t plus c. And suddenly that's a lot easier. We've sort of made something a little bit easier, perhaps. Let's go up here, and what do we do next? We want to get rid of these logs, so we're going to put everything to the power of e. So we're going to have e to the power of log w equals e to the power of minus 7 log of t plus c. And we're going to do the sort of same thing that we've done with these sort of things all the time. They just cancel out to leave w. This is what we want. How are we going to write this? We're going to write this as e to the power of the log of t to the minus 7, because that's that power thing. And because it's plus here, we're going to do times some constant, or e to the power of c. Because now that we're timesing them here, we add the powers. That's something that happens fairly regularly with these. Let's call this a different constant, bring it right out the front. We'll call it d. W equals d, e, and these cancel out, obviously. So w equals d t to the minus 7, or w equals d over t to the power of minus 7, which is a little bit nicer. It looks, at least it comes, and I may have to do a part 2 on this, but remember this is just v dash equals d to the power of, or d over t to the minus 7. And then we're going to have to do this whole thing again, because remember v dash is d v to t equals